morning. In this lecture, we discuss about the open mapping theorem. So, open mapping theorem is concerned with the open mappings. These are the mappings such that the image of every open set is an open set. More specifically, the open mapping theorem states conditions under which a boundary linear operator is an open mapping. As in the uniform boundedness theorem, we again need completeness, and the present theorem exhibits another reason why Banach spaces are more satisfactory than incomplete norm spaces. The theorem also gives conditions under which the inverse of a bounded linear operator is bounded. The proof of the open mapping theorem will be based on the Bayes category theorem. So first of all, we'll define what is an open mapping. So let X and Y be metric spaces, then T from domain of a T to Y with domain of a T is a subset of a X is called an open mapping if for every open set in domain of T the image is an open set in Y. So here note that if a mapping is not surjective, one must take care to distinguish between the assertions that the mapping is open as mapping from its domain into Y or onto its range. See here the onto its range is weaker than the into the Y. For instance, if X is a subset of a Y, the mapping X to X of X into Y is open if and only if X is an open subset of Y. Whereas the mapping X onto X of X onto its range is an open in any case. So the mapping F from X to Y is continuous if and only if F of inverse of A is open in X for each open set A in a Y. So this result we have already discussed up in a metric space. It does not give that F is an open mapping. That is, every continuous function may not be an open mapping. For example, if I consider a function f of t is equal to b sine t where t belongs to br, here this function, this maps, is continuous but maps from 0 to 2 pi on to minus 1 to 1. So we require some additional condition for this given by open mapping theorem. So what is an open mapping theorem or a bounded inverse theorem? A bounded linear operator T from a Banach space X onto a Banach space Y is an open mapping. And further, if T is a bijective, then T inverse is further if T is a bijective and T inverse is continuous, and thus we have it is bounded. So they will tell us about the relationship of the inverse operator and the operator T. So to prove up this theorem, we need the following lemma. A bounded linear operator T from a Banach space X into a Banach space Y has the property that the image of the open unit ball about the 0 and radius 1 contains an open ball about the point 0. So to prove up this lemma, we need 3 steps. In the first step, we prove the closure of the image of the open ball V1 centered around the point 0 and radius half contains an open ball V star. In a second step, we will prove that the closure of a T of a Bn contains an open ball Vn about the point 0, where Bn is a ball having a center 0 and radius 2 raised to the power minus n. And in the third step, we will prove that this TB node contains an open ball about the point 0. So first we will prove the part A. In connection with the subsets A subset of Ax, we shall write the alpha times A and A plus W as the collection of all those sets of Ax such that X is equal to be alpha times A, and A plus W is the collection of all those sets such that x is equal to be a plus w. These are just the scalar multiplication and the translation property over the set out there. Similarly for the subsets of y, we consider the open ball b1 about the point 0 and radius half. Any fixed x belongs to bx is in kb1, k times the b1, because it is a bigger ball now, which is a scalar multiple with the k, with sufficiently large k such that the k is greater than 2 times norm x. Hence x is the union of all those balls. And since t is surjective and linear, so we have a y is equal to be a t of ax, and x is equal to union of a k times the b1. So it is equal to be that. Because the t is a linear and onto this is equal to be union of a k times b1 is equal to be union of k times tb1 closure. So here we have noted that by taking the closure, we did not add the further points to the union, since that union was already the whole space Y. And by Barry's category theorem, we have, since Y is a complete, it is a non-measure in itself. Hence, we conclude that a closure of a TB1 must contain some open ball. So this implies that the closure of a TB1 also contains an open ball, say B star, centered around the point Y node and radius epsilon. So it follows that the B star minus Y node is contained in a TB1 minus the Y node. So now we prove the second step of this lemma. We now prove that the B star minus the Y node is contained in a closure of a TB node, where the B node is a ball centered around the point 0 and radius 1. So we will show that this by closure of a TB1 minus the Y node is subset of a closure of a TB node. So I consider point Y belongs to a closure of a TB node minus the Y node. Then Y plus the Y node belongs to be closure of a TB1. And Y node belongs to be closure of TB1. Hence there are Un, which is equal to be T of Wn belongs to be TB1, such that the Un converges to be Y plus Y node, and we get a sequences where Vn is equal to be Tzn belongs to be TB1, such that the Vn belongs to be Y node. Since Wn and Zn belongs to be V1 and V1 has a radius half, it follows that the norm of a Wn minus Zn is less than equal to be norm of Wn plus norm of a Zn by the triangular inequality we have, or using a property of a norm, is less than half plus half, which is equal to be 1. So the Wn minus the Zn belongs to be B naught. Further we have T of a Wn minus Zn is equal to be T of Wn by the linearity property of a T, which is equal to be T of Wn minus the T of a Zn, and T of Wn is equal to be Un, and T of Zn is equal to be Vn. So this is equal to be Un minus a Vn, and this Un minus Vn converges to Y. So Y belongs to be closure of a TB node. And since Y belongs to be closure of a TB1 minus the Y node, so we get closure of a TB1 minus the Y node is subset of a closure of TB node. Therefore, we have a B star minus the Y node belongs to a closure of TB node. So let Bn, which is equal to be the ball having a center 0 and radius 2 raised to minus n, a subset of Ax. And since T is a linear, so the closure of a TBn is equal to be the closure of a TB node over 2 raised to power n. And thus we obtain a Vn, which is a subset of a closure of a TBn. And finally, now we have to prove that it contains a point 0. So finally, we prove that the V1, which is equal to be B0 epsilon by 2 subset of TB node by showing that for every Y belongs to be V1 is in TB node. It is contained the point 0. So let Y belongs to be V1 for n is equal to be 1. We have a V1 is equal to be the ball having a center 0 and radius epsilon by 2, which is subset of a TB1, closure of TB1. And hence Y belongs to be closure of a TB1. So there must be a V belongs to be closure of a TB1 close to Y. Say the norm of Y minus the V is less than epsilon by 4. So now V belongs to be TB1 implies that the V is equal to be Tx1 for some x1 belongs to be B1. And hence the norm of y minus tx1 is less than epsilon by 4. So for n is equal to be 2, we see that y minus t x1 belongs to be v2, belongs subset of a closure of a tb2, as before we conclude that there is an x2 belongs to be v2 such that norm of a y minus t x1 minus t x2 is less than epsilon by 8. Hence y minus t x1 minus t x2 belongs to be v3 subset of closure of tb3, and so on the process will be going on. And in the another step, we can choose xn belongs to be bn such that the norm of a y minus summation of all these t xi's over the i's is less than epsilon by 2 raised to power n plus 1. So let Zn is equal to be x1 plus x2 so on xn, and since xk belongs to be bk, we have a norm of a xk is less than 1 over 2 raised to power k. So for n greater than m, we have the norm of a Zn minus Zm is less than equal to be summation of norm of a xk, which is less than 1 by summation of 1 by 2 raised to power k, which converges to be 0 as m converges to be infinity. Hence, the sequence Zn is a Cauchy sequence. Now, since the x is a complete, so this sequence Zn converges. Suppose that this sequence Zn converges to be x. Also, x belongs to be b naught. Since b naught has a radius 1, so the norm of x1 is less than equal to norm over the xi is less than equal to be a summation of 1 over 2 raised to power I, which is equal to be 1 by 2 plus 1 by 2, which is equal to be 1. Since t is a continuous, so t of a Zn converges to be t of ax. So the norm of a y minus the summation of a txk is less than epsilon over 2 raised to power n plus 1. So we get tx is equal to be y, and hence y belongs to be tb naught. So we get the result. So now we will come to our main result, which is an open mapping theorem. That is, we have to prove that a bounded linear operator T from a Banach space X onto Banach space is an open mapping. So now to prove up this, we have to prove that for every open set A subset of AX, the image T of A is open in Y. This we do by showing that for every Y is equal to be Tx belongs to be Ta, the set Ta contains an open ball about the point Y is equal to be Tx. So let Y is equal to be Tx belongs to be T of A. And since A is open, it contains an open ball with center X. Hence, A minus X contains an open ball with center 0. So let the radius of the ball be R and set K is equal to be 1 by R, so that R is equal to be 1 by K. Then K times the A minus X contains the open unit ball having a center 0 and radius 1. And now the above lemma implies that the T of a K of a minus X is equal to be K times the T of a minus Tx contains an open ball about the point 0. So now if T of K of a minus X contains the open ball about the point 0, so does the T of a minus T of X. And hence T of a contains an open ball about the point Tx. And since Y belongs to be T of A is arbitrary, so T of A is open. So now we have to prove that this mapping is an open mapping under this condition. So now we will go with the bounded inverse theorem. So bounded inverse theorem is going to say that if T is a bijective and T inverse is continuous, thus we have a bounded operator. It is. So it is very easy to prove it out. We have already done up results. So now finally, if T inverse exists, it is continuous because T is open. This result we have already done up. And since T inverse is a linear, so it is bounded. Thank you.